One of the comments that I got, is this loud enough? Is this alright? And can you understand me above that one? Yeah, I think so. One of the suggestions I got was to go back to a few of the tests because some questions were rather badly scored. The rest was going basically alright. I suppose most of you have seen it too. But some questions apparently were difficult or not easy to understand or something like that. And that's why I picked those out again. In test number 1, the question number 5 was the... Come on. There we go. Yeah. It won't work. I can try it this way. No. I'll have to do it like that. I will. So, the worst one was question number 5. That said, that question is basically, do you know what the sinc function is used for and what it specifies? It has nothing to do with transformations by itself. It is a transformable function, but it has nothing to do with the fact that you want to transform. So obviously that's not the right answer. It is not for cross correlation either. It is not for correlation in general. It has nothing to do with correlation. It has to do only with interpolation. It's this function that helps you interpolate if I have a regular equidistant sampling on the time axis or on a spatial axis, and I want the points in between. This is the ideal function, the most fundamentally right function to get all the other points out. So suppose I have conditions which are properly and theoretically correctly fulfilled for the Nyquist theorem that says that you shall sample more frequently than once over. You're right, it's a lot better. That you can sample at least, if you sample more than twice per inverse frequency, then you can recover the original function completely. And you do that by means of the sinc function. So it is used for interpolation. And that's the only correct answer. In the case of question 2, which was better understood apparently, but also there was something not quite right. Convolution of f and g has nothing to do with the correlation. Nothing, absolutely nothing at all. Nothing with the similarity either. And it requires the argument of f and g to go in the same direction. It positively does not. It has to go the other way, because if it does go the same direction, it is the cross correlation. And it's not the convolution. So the sign convention is the other way around. And it's that specific issue that distinguishes a cross correlation from a convolution. That's not the only one that had problems. On the second test, we again had question 2 and 5. I don't know why. Question 3 and 5. 5 again, the worst one, so let's look at that one first. A complex correlator. Does it require coherence? No, it doesn't. If you have no coherence, it measures 0. But it measures all right. So it requires only 2 signals as input, and it starts and gives a proper answer of the cross correlation of those 2 signals. Does it measure coherence? Yes, that's what it is. That's what it's for. Only works in the radio domain is bullshit. It works in any frequency domain. And is needed in convolution. It has nothing to do with convolution. So obviously that's not the right answer either. So there's only one proper answer here. Fourier transform, power spectrum. Is that an incomplete Fourier transform? No, it isn't. To be more precisely, if you want to relate it to the Fourier transform, it's the square of the Fourier transform, or more putting it even more precisely, it's the Fourier transform times its complex conjugate. It's the Fourier transform of a cross correlation. No, it is not. It's the Fourier transform of an autocorrelation. And is it even? No, it is not even. And I don't know why that is so difficult, but that's what comes out. And so, now the last one, question 5 again was the one that gave most troubles. The phase of a complex visibility is defined by the arrival time of the signals at the correlator. That was true until we had the correlator sit behind mixers. Then it was still affected by the arrival time at the correlator, but that's because I didn't do my cabling right and so on. But the real definition of where it happens is at the mixer, where I insert the local oscillator signal, and bringing the local oscillator signal out there with the appropriate phases at each of the two stations is the action that makes this thing work. Otherwise it won't even work, because the phase of the local oscillator at the mixer is the reference point with which I measure the phase of the incoming signal. As you realize, what you're doing with an interferometer is I'm comparing that wave and see whether they're in phase or counter phase. That's basically what you're doing. So I have a reference at each location to see the phase at that location, which I then transfer back to home so that I can read it. The rest of this mechanism is basically just a transfer of the signal so that I can read it. But the actual physical reference is the location of the telescope and the phase where I inject my local oscillator. So now we go back again. The phase of the complex visibility is defined by the arrival time at the correlator. That's not so. However, it is defined by the arrival time at the first pictures. And it is also defined by the UVW coordinates of the individual elements. Those specify the geometry of the sensitivity fringes that I'm projecting onto the sky out of my machine. Or putting it differently, I'm collecting, but it's defined by the topography of my receiving elements. That is the whole fun of the game. Otherwise we wouldn't know what we were doing. We are basically making an imaging machine out of some element here and some element there, and we're putting them in a phased fashion so together that they specify the source of the radiation. And so it does certainly also help in the definition to have a very precise calibration of the local oscillator phase difference between the two. And it is the phase difference that matters, of course. I don't care what the phase is at each of these two. That is equally good, and that is also equally good. It's the difference between the two phases of injection that matters. So that one is true. Now we go back to the question 3, which was not so difficult but scored badly too. I might have been the cause of the trouble to some extent, because what I sent to Jorge quickly was at C I had said false, and that's not fair. So we go back. Complex visibility is a periodic signal. No, it is not. Complex visibility is a measure of amplitude and phase, and has nothing to do with the periodicity in that signal. It measures the fringe with phase 0. No, it doesn't. It measures the fringe with an arbitrary phase. So it measures the fringe with an arbitrary phase, which is C. And therefore C is also true. And the complex visibility measures two cross correlations with phase difference of pi over 2 is of course the best specification of what a cross correlator is all about. It does measure it is a complex correlator which measures a complex number which is two quantities, one in one direction and the other in the other. You could call that cos and sine, or you could call that real and imaginary, or whatever you like. But you want a double number outcome to come out of that machine, and that comes properly about if you have one signal and another signal in quadrature. And that is what this thing is doing. That's what we're specifying indeed. Is this new in any way to you? Had I not explained that sufficiently well when we were at it, then I'm very sorry, but that was the idea that you would that was the idea that you got that point across. So I will still talk to Professor Suwaga about this one thing where I have sort of triggered him to misjudge you people, and that should hopefully help there. But for the rest, I can't see where I did something wrong in putting the questions. But possibly there is some trouble with English, but I didn't find that either. I realized that you have the problem that you have to answer an English question rather than a Spanish one, and I can't post a Spanish question, unfortunately. So you'll have to live with that. I can't do any better. But if you have questions about this, please make a point and make it straight now and here. I've tried rather carefully to not make the English too difficult in these questions. And I found more and more that actually the questions true or false are actually nicer questions than looking for the single best argument. And so I've given more and more your tests in terms of true or false. Basically that gives you the facility to answer more questions. And so the quality of the final experiment, the experiment is measuring your competence. The quality of that experiment, I think, has improved by doing that. That is at least the goal of the exercise. And I hope that you feel sufficiently fairly double-checked by my test this way, and you can live with it as we did. Okay, then let's go back to where we were yesterday. We decided yesterday that we would still look a little bit more at the optical interferometry, and we in particular went through the specific differences between optical and radio interferometry. Or putting it differently, we explained carefully that radio interferometry can basically always be done with heterodyne techniques, whereas optical interferometry cannot. We will have to live with the photons as they arrive. So the whole process of getting to the correlation and making the correlation must be done at signal frequency, and will happen with signal photons basically. You will see the photons arrive one by one by one by one. You will get the noise from the Poisson process of the arrival times of photons. And you cannot do anything more creative about that, because you pay dearly for that. Because what you can do with a heterodyne machine is you can first carefully amplify and thereafter wildly amplify if you still need more amplification. But it's the first stage of amplification that allows you to get a signal so well amplified with even eventually possibly other stages thereafter, that I always have plenty signal to split it without losing the quality of the signal. So I have now a core that has the signal, and if it's not sufficiently powerful to be divided, I amplify it, and I divide it then, and that is at no expense, as long as the signal input to the next amplifier is noise free enough to override the noise of this amplifier. And so a heterodyne system has the colossal advantage that I can use a single signal to correlate it with whatever I like. I cannot do that optically. If I like to correlate this optical signal with that and that other collection point, 3 baselines, then I must allow either beam splitting, or I must allow the fringes to be organized in such a way that you can do that properly with a triple correlation in one correlator. There's a trick to do that, and we haven't discussed that sufficiently yesterday. I think I should perhaps even draw the trick nicely here on the board. In fact, the proper way of correlating is I have a lens and I have a beam in here from one telescope and I have a beam in there from the other telescope. And each of these 2 beams goes down thereafter in the direction of the focus. And this one does too. And so right here, they cross at some inclined angle. They arrive there at some angle like that. That means that the wavefront as it arrived here and the wavefront as it arrived here have phase differences. And so they're constructive at one location, and a little bit further down they're at counterphase, so they extinguish. So the output of such a thing is like that. And that is within the patch of the image of these separate beams. I could put a third one in there to go that way as well. Then I get 3 different frequencies in here. I get the frequency that goes with this baseline, I get the frequency that goes with this baseline, and I get the frequency that goes with this baseline in this specific interferometer that I have now just constructed. I must only now be very careful in bringing the beams from the 3 elements of my interferometer, optical interferometer, into these 3 beams before they go into this correlator. But I can then check at each frequency, I can find the signal of each of these baselines. And then I can use photons effectively for more than only one single detection. I can use photons from this one for both the imprint it makes with this guy and the imprint it makes with this guy. So basically now photons are properly used, and that's the best way of going about it, the minimum noise trick. But still, it is not a complex correlator. It's a cos correlator or a sine correlator or an arbitrary phi correlator, because usually that's the reality, of course. You don't really know what the phases of each of these correlators, because I have messed it up somewhere else in the path length up to this point. But each of these correlators has at 0 on the meridian has some output of some phase phi, and I need the quadrature phi plus pi over 2 as well in order for it to become a complex correlator. There's only one trick in which I can do that, and that is in the delay lines that sit in front of here in these systems. Here's a delay line and here's a delay line. In these delay lines I must then make sure that this thing does piston across the whole fringe, and I read that sufficiently often, and then I can get all the signals throughout, and then I have a proper signal of the phase of the signal as well, and on top of the amplitude, which is just the fringe contrast. So now I have a proper fringe correlator that is complex by going in, by basically switching in time. I'm switching quickly from the sine to the cos and the cos to the sine, and sine to the cos and the cos to the sine correlator. In fact, I'm doing it more subtle, from the cos to the sine, to the minus cos to the minus sine, to the cos to the sine, to the minus cos to the minus sine. You piston like that right through. And that, if you do it sufficiently quickly, yes, there's a place. If you do that sufficiently quickly, then that is effectively simultaneous, and therefore out comes a measurement of a double number, an amplitude and a phase, or whatever you like. Well, we went through this yesterday. I want you to realize again that you have this problem of the coherence envelope that is basically defined by the passband of the signal. So you can judge already yourself here what the passband is, if you would know what the baseline length is in this correlation. If this were in the time domain on a single question, on a single channel, you could do that too. If this were the pattern of an autocorrelation, then you could say straight away that there's about 15 fringes from one side to the other. So there's about 1 in 7 is the ratio between the wavelength and the delta wavelength. So you have about a 15% bandpass. You can see that from this picture. If you would have 100 fringes in there, that would mean that you have only 1% bandpass. If you see only 3 fringes in there, you have a large bandwidth of well over a quarter. It's nice perhaps that we haven't seen yet and we haven't really looked at, but there's a way of seeing the difference in color. And then you can see straight away why the image, the fringe contrast goes to pieces at the end if I have enough passband, because you can see that they run out of phase completely and therefore they basically extinguish one another. There's a trick to make that even more attackable, and will allow you to have different passbands next to one another, and you'll see that like this. If in this direction I have my fringes, then if I have that in a slit, so I make the image of these beams in one way much narrower than in the other, and then I have a dispersing element in there as well, then I can have a picture like the one above. And I have the different frequencies next to one another, and then I can sum later, and then I don't need to extinguish what you would otherwise do. It's basically what is intrinsic to sort of a correlator. Yet another way of putting it, yet another time. So you can see straight away that correlation envelope and bandpass are truly each other's inverse. If you want very much bandwidth, which you do because it gives more sensitivity, you get more light, then at the same time your tolerance of being correct with the delay line gets to be much steeper. That is just a set of measures that demonstrate that it can be done, and you can actually this way measure the size of the distance to the first zero. It has been very successfully measured at about this location, which says that I have one fringe every 1/66th of an arc second, 66 fringes in an arc second. And that says that apparently this star, Alpha Boötis, has an angular size on the sky of about 30 milliarcseconds. That's the way you can actually get stellar dimensions. Mind you, that is not trivial. It used to be fundamentally impossible until the early 60s. We did not have any stellar diameters except indirectly, theoretically. We had distances to stars, we had the luminosity, we had the temperature, and as you know, the temperature of a star specifies its luminosity per square meter. According to the Stefan-Boltzmann law, you get sigma t to the 4th power per square meter as power out of such a star. So as you know the size and the temperature, you know the power in total of that star. And so you can calculate its size if you know the distance as well. And that was very interesting to try and do, so we did want very good distances. I'll come to that tonight in the lecture about astrometry. But it's good to realize that one of the things that you would very much like to have is verifications on that sort of theory and see whether the diameters that you now specify are right, because this sigma t to the 4th is a statement that only is right for all wavelengths at the same time. So it's an integral across all wavelengths, and the stellar spectrum is not very much like a Gaussian, Planckian usually. The temperature in the upper layers of the atmosphere and in the lower layers is much different because the heat comes from below. And at some time the atmosphere becomes sufficiently transparent for some wavelengths but not for others. And it still radiates from every layer where it can. And it's all over the place, so the temperature distribution now becomes weird in the atmosphere. And at separate wavelengths you look at different levels of the atmosphere. That's the very cause for the line profiles in stellar spectra. And at the same time, of course, therefore the integral over all wavelength is not so easily specified with a single temperature. And so you can see that it is very valuable to get stellar diameters, and this is one of the apparent successes of that sort of work. What's interesting is that this is with 2 telescopes only, and that's just about all you can do with 2 telescopes. You cannot specify much more about that star than the fringe comes down and actually hits 0 at such and such a distance, so at this period of your fringe. If I do it better and I do 5 telescopes, then I get a true image. I can sort of compose, I can superimpose with 5 telescopes, I can superimpose different position angles. I can get something that looks like a beam. And as you know, we can then get the antenna pattern of such a mapping beam precisely. We can calculate that because we calculated the map as well. And so you can sort of deconvolve that image and find out that it is indeed a disk sitting inclined. If I can even go more and have as much as 21 telescopes, then you can actually have a complex image. And you can make pictures with many more pixels across the whole source. This is about our triple correlation or closure phase. We specified that you can just get a single closure phase out of 3 baselines. So you would have wanted to have 3 phases. Instead you got a single phase difference because the reference point is not even defined anymore. So that is rather a significant loss of phase information. That significant loss gets better and better the more telescopes you use. And you get about 90% of all phase information out if you have 50 telescopes and you do all the baselines. It's good to know that. So if you get enough baselines, this very loss of the fact that you haven't got the phases right is not so bad as you might first think. You get a picture that is basically reducible and transformable properly, apart from the fact that you don't quite know where it lies. So you have to have other means of positioning it properly on the sky. Closure phase will never do that for you. But it's good to know that you can, a good image that is rather model independent in the end, as long as you allow it to sit at an undefined location. The problem is you have to do it in an iterative approach. There's no straightforward open loop software for it that says you use your closure phases like that and then bang comes out the Fourier transform with these and these defects. No. You try something and turn that into autocorrelation because you sort of derive phases. If you have derived these phases that specify something about the elements, about the errors that came from each of the elements. And in doing so, you get n times n minus 1 baselines out of n telescopes. So you get very many phases for much fewer elements. So you can now sort of interpret all these phases that you now have induced, sort of guessed up from a model. You can allocate from that the error to each of the elements separately and say, oh, but then that must be that telescope number 5 had a phasor error of so much. And if I put that much back up, then the phases all fit much better. You do the game iteratively that way, and that improves your model description, improves therefore the description total, and the closure phases will fit better and better. And that way, iteratively, you get to the final result, implying at the same time that you know much more about the instantaneous errors of the individual elements, which is the trick of using the image itself to see what was illegal in your machine. And that's helpful because that way you can sort of calibrate on the basis of your data rather than on the basis of a separate calibration observation, which is very good. So that's what it's all about, this trick, and this self-calibration actually.
What's the array with the most telescope? Is there a
Optically, we've gone to 6.
6?
Yeah.
You need radio?
And in radio it is the VLA, which has 27. Plus outside stations that you can couple to it. And if you keep going that way, then particularly VLBI has, of course, a colossal number. It's just a matter of bringing back the signal, putting it nice on store, and get going on calibrating or correlating. And then you can make more and more and more. And indeed, you point that out, that it's interesting, because this VLBI is the example par excellence where we, of course, cannot possibly have absolute phases. We cannot have the right phases. We can only live with closure phases there. So it's a very good thing that you can get better and better images by bringing in more telescopes. But it's fascinating that self-calibration helps you finally, from the data itself, to specify the illegal effects and turn them into understood defects in my machine, so that the picture gets better. Because otherwise you would have negative flux from the sky and that sort of things. You can just find out that that must be illegal, and by all these things that cannot happen, that you can find by trying to stick a picture together, you get more and more. Oh, telescope 17 must have been so much off in phase for this hour, so something by in the atmosphere and then it went back again. And that sort of things you can find out of the data that make your own picture. And if you do that well, then you can make this difference. The picture of the source without closure phase and the picture with closure phase. And you see that's rather a lot more physics than that one. Now we know what we're talking about and what we are trying to understand, because what this thing obviously is doing, it is spraying some signal, some material outwardly while it's rotating. And you can see the whole spiral that is caused by that. Whereas in that case, we don't really know what this thing is doing. So it's awfully much more physics if you get the asymmetric part of the image as well healthy, even for small images. This is only 5, 6, 7 pixels across, but it is already extremely telling about this source. Then I want to go to this fascinating infrared Heterodyne interferometer. Was devised on the basis of a publication in 1974 by, among others, Charles Towns, who got a Nobel Prize in late 60s for something else in physics. I didn't check it, I should have checked it, but it was on something else. He's been very active since, mainly on interferometry, and he's still alive and still active with his machine sometimes. He's 99, was born in 15. And there they were doing the first experiment on the Solar McMath telescope. This is a sun telescope in Tucson, Arizona, which is built so that the beam comes down with a set of mirrors all the way up. And the beam therefore always goes down the same pipe, regardless of where the sun is sitting. And then at the bottom of the telescope, right in here in the soil, they're having a reflective telescope that makes an image which then gets projected back onto the table basically, so they have a sizable solar image. But you can also use the same telescope on stars, and he could therefore then use a little beam and another little beam out of that telescope in the same way we did it first on the Hooker telescope, where they brought this light in. Michelson, I showed that picture to you. He could do that but on a smaller aperture, but at least demonstrate that his idea of making a heterodyne optically would actually work, and that he could correlate those signals and would get the proper signals out, the ones that he expected. They have been doing much more with that. are having a similar sort of setup with a siderostat. So you have a drive which is pointing the beam into a horizontal telescope that sits horizontally. And that puts the light on the correlator. And that's quite big size mirrors, they're 1.5 meter size. And he's made observations with that are quite good. You can see straight away that the atmosphere does something. I've a bit already enlarged it so that you could see how with time it fluctuates. This is a whole 2 hours. So you can see how this fluctuates with time to fractions of a minute. You can see that it moves of the order of 2 stripes at the side, and that's, each stripe is a micron. So that's what the atmosphere is doing, and you get a feel for the speed at which the atmosphere is doing the slow but bigger variations, and the smaller ones you can't quite see yet. And then you must better explode the data. And he could demonstrate that he could indeed see the fringes of Betelgeuse. In your homework I suggested it would be 0.15 of an arc second. The real number is better, like 0.05. And what he's doing there is again this CO2 laser heterodyning with the incoming radiation, so that he gets near to the CO2 laser frequency, he gets the proper fringes out. And that's just to see the team. Charles Towns is this person here. When we got started participating together with Leiden, he came and was one of the key people of our workshop on interferometry in Leiden. And he looks basically still like that. He's there a bit younger, about 15 years younger than today, but he's still going strong. And they're moving to a new site here. And that's the sort of setup with a 3-beam system. It's still rather compact, so that he can at least have his closure phases completely done in a triple system. And that's the way you have to stick it together complexly. But again, this part is the part that you usually also have for any radio machine. And it's only the upper part here where you make sure that you have the laser properly phase locked from one to the other station, so that the phase reference on all the 3 stations is defined by your system. That's the hard part of the story there. And then you can make it work. What it then works for in particular, of course, is that we finally can get sizes on the main sequence, and we get to know true stellar sizes. It's one of the first things. There's an old slide in selling the issue. Yeah, go ahead. And that's model-wise the sort of stars you're looking at if you're looking at very cool, very big stars. Myra supposedly has convection cells that are as large as a larger fraction of a quadrant on this thing. In fact, that's an idea that most of the stars that are almost truly convective to the core, you have that the convection cells grow very, very big. The convection cells on our sun are very small. They're of the order of a few arc seconds. On a sun where that is 1800 arc seconds across. So it is very narrow stochastically, but that's not so for stars that have a convection zone that is from much and much deeper inside the star. And then you get these very big convection cells, and that would be very interesting to study too, because then you're doing basically geology of that star. But it also at the same time tells you much more about the mechanisms of convection that we have not very good theory for, and so we must observe a lot about convection in stars to get that part of the story better worked out. It helps you also to get the size of the star as a function of wavelength and see that the star particularly at a longer wavelength, where it basically is the same star, but then further out on optically thin area where you can look through the dust shell that is forming around the star, where the star is basically smoking, blowing its own material out. In the last phases of the asymptotic giant branch, stars are losing mass at terrible rates, up to 10 to the minus 6 of a solar mass per annum. So that's enormously strong outward wind from the star, and in that wind the density at relatively low temperatures like 1000 Kelvin or even lower, the density is so high that dust can form, and so this star is basically smoking, and that's the main source in fact of the interstellar dust. And in that process, of course, the dust becomes a flux converter. A photon, a hard photon, visible or even UV photon hits that dust. Surely it hits the dust because therefore the star cannot shine outwardly because there's all this dust. But that means that the dust gets warm, and so the dust radiates at much longer wavelengths, like 5 microns or 3 microns. And we can measure the star being big, although we can look right through those layers to some extent. But all that does is temporary, a sort of flux converter. In fact, you can see that from these stars. That type of stars usually has a spectral energy distribution, which is a bit like this. This would be the regular Planckian, and at a longer wavelength it does this. And this is the part that is caused by energy conversion from the harder photons here, absorbed and re-emitted in the infrared, in the far infrared. And so you can see the presence of dust around stars and also in galaxies by observing an excess infrared radiation. He thinks it's too warm in here, I suppose. That's sort of true. I'll go a bit quicker now, because otherwise I'll mean to close. I actually meant to see that, but I wanted you to see a few more pictures. There's a nice picture of the size measured from Betelgeuse at 11 microns. So that's almost your homework. And this is very nice too. This is the housing of the Cambridge Optical Astronomical Science telescope, a synthesis telescope. And so it's the first aperture synthesis machine in the optical.
Excuse me, I have a question. I don't understand very good, but that curve shows Planckian.
Yeah.
Yeah, so that part is for the noise and the dust, and that other things that makes the Planckian up.
This is, let's say, 0.5. Let's make it big, a bit cool color. So look, this is of the order of 1 micrometer.
My question is about what happened. We see that curve, but we know that it's a Planckian. So that part we learn from what happened with that curve.
What happens is, I have a star, and that star has wind blowing out. And in that wind, the density is so high and the temperature gets so low that it forms dust. That dust makes the environment of the star opaque, so the light cannot leave anymore. Instead, it gets absorbed by this dust. So the dust gets warm. The dust further out at the radius of, say, where the temperature would have been 500 K, the dust gets 1000 K just because it gets heated from the flux that it gets from the back. And that extra temperature makes a star which is much bigger at 1000 Kelvin. And so at a lower temperature, for a much lower material, at that much lower temperature, the star grows bigger and bigger, and therefore it shines much harder than it should have done had it just been a standard thing with a single temperature. So the star, going to a longer wavelength, becomes a bigger star at a lower temperature. And that is a signature for stars that are losing dust. That causes infrared excess, and that's the way you can recognize the stellar winds that produce the interstellar matter in the dusty component. The first optical machine to actually give some data that would possibly in the end produce phase closure images was the Cambridge Optical Aperture Synthesis Telescope, thought of in 1984 and in 1982 and funded in 84. Was invented by a radio astronomer who had been spending most of his life on this aperture synthesis. In fact, there you have the two telescopes of the 1 mile telescope that was the first one to run aperture synthesis, Earth rotation aperture synthesis, in the early 70s, no, in the mid 60s. And John Baldwin, who is the originator of this idea, was already working hard on the 1 mile telescope at the time. He was there at that team already. So that is the first one that actually made this trick work through phase closure, thereby making optical aperture synthesis possibly a useful system. And it's nice to have these pictures, like for instance also their delay tunnel. They have this enclosed thing with a lot of dirt and insulation over it in order to make sure that the temperature inside is very stable. Very much like the delay tunnel for ESO, where we have in the delay tunnel also much insulation around it and make sure that the temperature there is very stable. In fact, that is one of the sources of the sort of failure at ESO. They have troubles making the interferometry work. The tunnel is not sufficiently stable because there's too much outside air just blowing through. And they haven't got here. They have much more made sure that the air from outside does not go in and out, so that this thing is a thing of its own with its own temperature. And so the temperature can only very, very, very slowly change. And the diurnal change is basically absent. Just to get a feel for the very complex machines that you get if you want to do a 6-element beam combination, you get a table full of all these elements that basically do the matrix of re-switching of all the beams that they get each at the right place. So it's just basically a very complex issue, a table full of optics. That's what it boils down to. What is interesting too is to have a demonstrator of the astrometry that you can do with it. It's a bit exaggerated, a bit early calling out that it's going so well, yet at the same time it is not so bad. You see these data points and you see them enlarged here, you see the uncertainties per piece, and you can, what is measured there is the distance between two stars. So it's the distance in terms of fringes from one star, a reference star for phase referencing, to another star. So this interferometer is basically looking at two stars at the same time. Not quite, it's switching all the time between the two stars. But it switches so quickly that you might hope that that works, and that's the way you get these data points. And you can see, I hope, that the certainty of these points is much better than 1 milliarc second. This is 2 milliarc seconds. So there's sub-milliarc second astrometry that is not trivial to get these things done. We said that for fringe tracking, you need to use a reference of another star. And then you need to extract two beams out of a single image. You do that with a star separator. That's pretty close to a very complex machine in itself, as you can see. That's the star separator for the auxiliary telescopes of the ESO VLTI. This is the top-down view. The optical axis comes in here, and then it gets split via this mirror here to two beams, and that gets reconditioned and then sent to the main delay line. You see how much additional optics comes in there, and this must be extremely stable and well specified, otherwise it won't work. You can see the thing from its side to its two levels even. And these thick beams are the ones that go to delay lines. Another worry that you might have is the worry about the phase length of your delay in a tunnel filled with air. This is to show you that the dispersion causes phase variation over a fixed length of time and of distance of radians, unless you get into the wings of the waterline, and it gets all over the place. So phase referencing from one star to another needs to specify how you make the weighting of, for instance, let's say you do fringe tracking here, but you're looking at the star between 2.4 and 2.2, and then this offset is already something that you must properly bring into the account. So you must take into account that the total length of the path, the optical path length through the tunnel, is significant fractions of a radian different at one wavelength than that at another wavelength. It's the same thing that you have also with radio signals on cables. Propagation length along the cable is different for different frequencies, so put a pulse in, at the end comes a sweep. And the same thing you have also in the optics. Going quite the other direction, to the longest wavelength that we're playing with nowadays, here we have an observation with LOFAR, which is a very new, very large array of for very low frequencies and long base wavelength. And there, of course, it's very difficult to get high resolution images. This is a picture of the Whirlpool Nebula. You can see that here we finally get again to a resolution of few arc seconds, and that at 2 meter wavelength, that is a colossal telescope. If you get 5 arc seconds beam, then you have apparently a baseline of 40,000 lambda. 40,000 times 2 meters is 80 kilometer baseline. And that works as a synthesis machine. That's nice. And it's particularly nice if you think of the fact that we are now doing it at 2 meters, where the ionosphere has a mind of its own and puts in another radian of 5 that I want to get rid of completely before I can get a nice image. So I must repair that. Well, I thought that was rather a nice one, because that's the image of the 21st of August. So that is of the end of last week, to demonstrate to you that these developments are still ongoing, and that we are getting to the point that we can get again on top of the longer wavelength as well, which was a hard thing to do because of this terrible ionosphere. So basically, as far as I'm concerned, I have sort of given you a global overview introduction. I'm not particularly hopeful that you have developed in 1 week into full-fledged interferometrist, but if I'm successful, I've told you enough about interferometry that you know what the sort of problems you will face if you were to go and work with it, and you know also how believable it is that it shall work also through your problem, so that if you get excited about it, just get going and do it. So I hope that's the point I got across. Thank you very much, and I found it very, very exciting to be here and to talk to such very eager students. That's fun. So I like that a lot. Thanks a lot. I'm very pleased you could live with my English.